We are now in the trigonometric identities and equations unit. In this unit, we're looking at how trig ratios and expressions can be equivalent to one another. And when they're equivalent, that allows us to do replacements in order to simplify expressions. And it's also useful for us when we're trying to solve equations. So with these kinds of tools, we can actually solve more involved equations than we've been doing as well. This first topic is looking at the compound angle formulas, and you'll see them in the Minds On. There are going to be a number of relationships like this that you're going to be provided with, and it's helpful to be able to memorize them. The majority of them will be given on the test, but it really is more advantageous to know them in your head. So when you're doing the work, it will allow you to simplify the problems faster and be able to identify what replacements to do much easier. So with the Minds On, you'll see here that I am encouraging you to devise a strategy for memorizing the compound angle formulas. It'd be a good idea for you to stop right now and think about how you could memorize them and see if there's any kind of patterns that could help you in remembering them. I'm going to share with you what I use to help me remember them. So looking at the sine A plus B and the cos A plus B, the sine A plus B, I think of it as sine cos cosine. And notice in all of these ratios, A and B are in the same order all the time. And then the cos relationship, cos A plus B, I think of that as cos cos. And so I know it's cos cos sine sine. And then the tan A plus B, notice that it's tan A plus tan B in the numerator, and then it's 1 minus tan A times tan B. So that helps me remember this. And then notice with the subtraction formulas, they are basically the same pattern, except you got to watch for the signs. Notice that with the sign ratios, the plus in the brackets here is also a plus in the middle of those terms. Over here, there's a minus in the middle in the brackets, and there's a minus over here. Looking at the cos A plus B, you'll notice that the signs are different between what's in the bracket and what's in the actual expression. So that's the other tool that I use to help me remember. So I get in my mind that with sine, the signs are the same, and with cos, the signs are different. So for sine, we have sine, cos, cosine. Whereas with cos, we have cos, cos, sine, sine. And then notice with the tan A plus B, once again, similar to sine, its signs are different when you look at the numerators. However, with the denominators, they're different. So you have a plus in the numerator, similar as what's in the bracket, but then you have the opposite sign in the denominator. And so when you look at the minus, you'll see there's a minus in the numerator, and then there's a plus in the denominator. So I would encourage you to just work on memorizing those as we go through this unit. So now what we're going to do is simply apply these. And usually I encourage students to try these on their own. So basically, the goal is that you would match these with the patterns in the expressions given here. If you look at the tan identity, you can see here that this pattern is the same as this pattern here. And so what we want to do is take what's in place of A and B, in this case pi over 2 and pi over 4, and replace that inside of this side of the expression, and we can come up with a simpler relationship for this. So I would encourage you to try doing that on your own with both this expression and this expression here. So I know from the identity up above that this is equal to tan A plus B, where A is this first angle here, and B is this second angle. So all I need to do is put pi over 2 in here plus pi over 4, similar to the expression up above, and then simplify. So I'm getting a common denominator, tan of 2 pi over 4 plus pi over 4. Simplifying, we get the tan of 3 pi over 4. So basically, this expression here can be boiled down to something much simpler. And hopefully you can see how that would be helpful. Coming over to this cos expression, notice the pattern cos. So I know that is the cos formula, either addition or subtraction. So I'm looking at the sign in the middle, and I see that the sign in the middle is positive. So that means I'm working with this one. By the way, I did not focus on the signs here with this tan addition formula, but notice that the plus here was the same as the plus there, so I knew it was the tan of a plus b as opposed to this one. So we're going to use the cos a minus b subtraction formula. And once again, I see that a, remember they follow this pattern, there's a consistency here in the way we write them. A is the first number and b is the second number. So what we want to do is the cos of a minus b. So this equals the cos of a minus b. And once again, we want to simplify that. So we need a common denominator, which looks like it's 12. So we have the cos of 6 times 2 is 12, so 2 pi over 12 minus 3 times 4 is 12, so 3 times 3 is 9 pi over 12. And then we will subtract those. We end up with the cos of minus 7 pi over 12. And I would reduce that if it were possible. In this case, it's not. And now we see that this expression here can be boiled down simply to the cos of minus 7 pi by 12. Something else we do with the compound angles is we use the special angles in order to take an angle that normally would give us a decimal answer and break it down into two parts that are both special angles, so we can use our special triangles and exact values. So you'll see here that I've given you an example that relates directly to this one, and then I just gave you another example to consider. Something I haven't given you so far is examples of the pi ratios. So let me give you one right now. We could have 7 pi over 12. And there are a number of ways we could break this up. 5 plus 2 is 7. 4 plus 3 is 7. 6 plus 1 is 7. So the goal is to find two numbers that will cancel into the 12 such that we have one of the special denominators that we're used to. Think about the special angles that we have. Pi by 2, pi by 3, pi by 4, pi by 6. These are all exact values, and then there are multiples of these. Basically, if you have any expression or any fraction that has one of these in the denominator, regardless of what's in the numerator, then we will have a special angle to work with. So in this case, if I did 6 and 1, for example, the 1 pi would still leave me with a 12 in the bottom because the 1 won't cancel. So in this case, what would be helpful to us would be something like 4 pi plus 3 pi. So if we have 4 pi over 12 plus 3 pi over 12, notice that when I simplify those, I end up with pi over 3 plus pi over 4, and both of these are our special angles. So coming down here to these two examples, we just saw in the example above that the sine of 75 can be written as the sine of 45 and 30, which are special angles. And now we can use our compound addition formula for sine and write out the ratio. So this goes sine, cos, cos, sine, and the same sign in the middle. So sine of 45 times the cos of 30 plus the cos of 45 times the sine of 30. And then we use our special triangles. Our special triangles are the 1, 2, 3, and the 1, 1, 2, which is an isosceles triangle. I want to try to draw those sides very similar. I'm going to make it a little bigger so I have a little more room. So we have the 1, 2, root 3. This would be 30. And this would be 60. And we have the 1, 1, root 2. And both of these would be 45. So I only need one of them. Coming back over here, the sine of 45 is the opposite over the hypotenuse, which is 1 over root 2. The cos of 30 is the adjacent over the hypotenuse, which is root 3 over 2. And I shouldn't have put a plus sign in there, so let's get rid of that and put brackets around these. Plus the cos of 45 is the adjacent over the hypotenuse, 1 over root 2. Times the sine of 30, which is the opposite over the hypotenuse, which is 1/2. And then you use your skills with radicals and fractions in order to simplify these. First of all, I have root 3 over 2 times root 2, or 2 root 2, plus 1 times 1 is 1, all over 2 times root 2, which is 2 root 2. And in this case, it works out nicely that they are common denominators. So what we have is root 3 plus 1 all over 2 root 2. Now at this point, we don't want to forget that we need to rationalize. So we need to multiply the denominator by root 2 and the numerator by root 2. And keep in mind, when you multiply this numerator, it's distribution. So it's a good idea to put a bracket around there to remind you of that. And so we end up with root 2 times root 3 is root 6, plus 1 times root 2 is root 2, all over 2 times root 2 times root 2. Well, root 2 times root 2 is undoing the root, basically. So we end up with 2 times 2, which is 4. And now that's complete. And those are not like radicals, so these cannot be simplified any further. And that's it. Now looking at this next one that's in radians, one thing to note here is that in reality, this is probably not the best example because of the fact that this has a 2 in the denominator, which is one of our special angles. It's an exact value. So it turns out that this could be evaluated as it is. Still, I'm going to go ahead and write it as the sum of 2 other angles and use the compound formula just to illustrate the point. So there's lots of choices here of what I could do. So I'm going to end up doing the sine of 2 pi over 2 plus 9 pi over 2. And that adds up to 11. And that ends up giving me the sine of pi plus 9 pi over 2. Now notice in this case, I have angles that are not acute. So I actually will need a diagram as well in order to be able to answer these questions. So we'll do that in a moment. First, let's write this out. Once again, this is sine, so similar to the other one, we would have the sine of pi times the cos of 9 pi over 2 plus the cos of pi times the sine of 9 pi over 2. So at this point, to do the sine of pi, I will need a diagram. So I'm going to draw my diagram over here so I can leave room for the rest of the work. So if we're talking about pi, then we're starting on the positive x-axis and we're rotating to here. That would be pi. What that means is that our radial arm is right here on this axis, and normally when we're on this axis we use 1 for its length, and because we're on this side it's minus 1. So in this case, the opposite side, which would be over here, is actually 0 because it's flat on this line, and the adjacent is minus 1 and the hypotenuse is 1. Now I can draw a hypothetical triangle for that where I'll draw the opposite side very small, knowing that in fact it's 0. So this would be 0 over here. This is minus 1 on the axis, and then this length here is also 1, but it's positive because it's the hypotenuse. So the answer to sine of pi then is 0 over the hypotenuse, which is 1. So the answer here is 0. And in effect, whatever answer we get for this ratio really isn't going to matter because this is 0, but we're still going to fill it in. So we're being mathematically correct here and that we have clarity in what we're doing. So with the 9 pi over 2, that's 9 pi over 2's. Every quarter is a pi over 2. So that would go once around. That would be 4 pi over 2. If I go around again, that's 8 pi over 2, and then one more takes me to 9. So 9 pi over 2 is on this axis, and once again we're going to label this side length 1. Now in this case, the adjacent is 0, and it's the opposite that's 1, along with the hypotenuse. So this hypothetical triangle would look something like this, where in reality, the bottom leg or length there is the adjacent. That's going to be 0, whereas each of these will be 1. So the cos of 9 pi over 2 is the adjacent over the hypotenuse, which is 0 over 1, which is also 0 then, plus, now we can refer back to the diagram we've already drawn for cos of pi. So on this axis, the cos is minus 1 is the adjacent over the hypotenuse, which is 1. So we have minus 1 for the cos of pi. And then finally, sine of 9 pi over 2. Looking here, we have the opposite being 1 and the hypotenuse being 1. Look at this hypothetical triangle. The opposite is 1 and the hypotenuse is 1. So 1 over 1 is 1. And now simplifying, the answer we get for this relationship is minus 1. Now, what we could do is, remember that this blue line went to 9 pi over 2. in order to just check our answer there, we could, since this one actually is an exact value, even though we've chosen to do it this way for illustration, if I go two more, so 9, 10 pi over 2, 11 pi over 2, notice that if we did sine, the opposite is down this way, and it would be -1, which is the answer we got here. So that's a good verification that this use of the identity worked correctly. Now the other use, finally, of a compound angle formula and any of these other identities that we have is to prove the equality of two functions or the equality of two expressions. And that's what we'll be doing in a lesson later on, where we look at purely trig identities and trying to prove that one expression is equal to another. Once again, one of the values of that is being able to simplify expressions to easier form, as well as it's useful in the idea of trying to solve. If you know that two items are equal to one another, you know from other algebra that you've done and solving equations how that can be useful. So what we want to do here in order to prove these to be equal, I want to remind you first of all that you should always write left side and right side. And I will say that in the textbook we use, there is an error back there where on many questions they cross over between the two, and they shouldn't have done that. That is a very significant error. So we're starting with cos x on this side, and we have the sine of pi over 2 minus x on this side. Now, you're going to learn later when we spend more time on proving expressions to be equal using trig identities that it's often much easier, and typically what we will do is start with the more complicated looking side. So we're going to start with this side. And notice here that we have a subtraction identity using sine. So we're going to expand that out in order to help us to simplify this. So the sine of pi over 2, and you can look back at the identity to remember. So this goes sine, cos, cosine, and the sign in the middle is the same as what's in the bracket. So we have sine pi over 2 and the cos of minus x minus the cos of pi over 2 and the sine of minus x. Now the sine of pi over 2, once again we can draw a diagram. Pi over 2 would be from here to there. This length is 1, and remember the opposite and the hypotenuse are both 1, and the adjacent is 0. So in this case, sine of pi over 2 is 1, and we have the cos of minus x minus the cos of pi over 2, so the adjacent is 0, over the hypotenuse, which is 1, which leaves us with 0. Sine of minus x. And what we have here now is the cos of minus x, and that's minus 0 times sine of minus x, so there's nothing here. Now these two expressions are not completely identical yet. We have a minus x in front of the cosine. So in order to deal with that, we're going to use our knowledge of what this ratio looks like when it's graphed. So we're going to take a moment and just graph a cos curve. And so we're just going to do a quick sketch here. So I'm making these into quarters. And then sine and cos, their parent functions both go equally above and below the x-axis, and they go up to 1 and down to -1. And in terms of radians, this would be 2 pi, pi, pi over 2, and 3 pi over 2, pi over 2 minus, and then minus pi, minus 3 pi by 2, and minus 2 pi. Drawing this, what we get is a cos starts at a maximum, axis, minimum, axis, maximum, and same on the other side, axis, minimum, axis, maximum. Now in the future, you don't necessarily have to draw these diagrams if you already know the relationship from your familiarity with these graphs. But just notice here that when I do a minus, think of your transformations, that's a horizontal reflection across the y-axis. If I take this graph and horizontally reflect this half over to this side across the y-axis and then reflect this over to this side, notice that they each fall on top of each other. So in reality, the cos of minus x looks exactly the same as the cos of x. So that means that we can simply write here the cos of x, and now we've proven that the left side is equal to the right side. And that's it for this lesson. You can go ahead and practice using these identities.